Hello everyone, my name is Another Man and welcome to a little series on this channel that I would like to call Optimizations in C++. So this is going to be a brand new thing and we're just gonna goof around a little bit. But basically what I want to do in this series is I want to make a ray tracer, which is notoriously pretty slow, especially when done on the CPU exclusively. And from there, I want to go ahead and explore some optimization possibilities within C++. So we're going to be talking about things like cache and memory alignment. We're going to be talking about heap versus stack. We're going to be talking about stuff like SIMD. We're going to be, of course, talking about algorithmic complexity and multithreading. All sorts of stuff, anything that we can possibly do to make our ray tracer as fast as possible. The only exception that I want to make here is that I will not be using the graphics card for this, because of course we want to make a C++ optimization series and not necessarily an OpenCL optimization series. Maybe we'll do like a bonus episode on graphics card, but we'll see. And before we get started, keep in mind that a lot of these optimizations that we'll be talking about can also be applied to other programming languages, but not all, right? So we'll be using C++, but some stuff like SIMD you can also apply to C#. Just keep in mind that if you're really looking for pure optimization, a managed language like C# is probably not the right choice. Use something like C, C++, or Rust. Okay. For the first episode here, we will actually be setting up our ray tracer, so we won't be doing actual optimizations just yet. That is why this is kind of a episode 0, but it is very useful nonetheless, because of course, once we start optimizing, it is really useful to actually know and understand what you're optimizing. So writing our own ray tracer here, although it will be very, very simple, I assure you, it will help us tremendously to understand what's going on and what we can do to optimize in the later episodes. Alright, so let's get started. Okay, so let's have a quick look at our code here. I've already prepared a whole bunch of boilerplate stuff, like all of the OpenGL stuff, the window, so you don't have to worry about any of this. It doesn't really have much to do with optimization anyway, right? It will take a very, very long time before the rendering actually becomes the bottleneck of our program. So nothing to worry about here. If you want to have a look at this code, you can go to the GitHub page linked below. And of course, you can do anything you want. Keep in mind that we are using GLFW and GLEW as our libraries, but nothing else. Not even a math library, which is something that we will come back to in a second. But yes, for all of our windowing stuff, we initialize GLFW, right? We create a window, we initialize some sort of renderer and ray tracer. We'll get to that in a second. Then we just render all of our stuff in a loop, right? Until the window should be closed, and we time how long every iteration of this loop takes. Simple enough, right? Now our renderer is also pretty simple. It just has some shaders in it, and we just create a texture. A quick shader, we create a quad with vertices and UVs, and then in the end we render this quad using some sort of byte array, right? And this byte array will be filled with colors that we put in the texture that we render onto the quad. In other words, we are going to be filling this byte array. Yes, so for every single pixel on the screen, we can write to this array just a color value in RGBA. And that will be, of course, our ray tracer. For maths, I have created a very basic linear algebra library that just defines what a vector is. And that's basically it, all that we need, at least for now. Keep in mind that I'm not using a maths library here, but instead something that I wrote myself, because at some point I'm sure we will find that one of our bottlenecks might be maths. Now, if we use a library, we can't really change it up that much, or at the very least, it will be difficult. If we write our maths ourselves, this will be a lot easier. So that is why we are doing this, at the very least for demonstration purposes. If you find a good library on the internet, like GLM or Eigen, then sure, go ahead and use it. It's very well optimized, so if that's the bottleneck, then I think there is very little you can do. Okay, let's look at the ray tracer now. So this one also very simple. We're just loading a mesh, which is just vertices, right? We're not giving any colors or normals, anything like that for now. Just vertices, we load them into these vectors, and then here in a run, we can do whatever we want. We can actually run the ray tracer using this geometry. Right, for now, we are just looping over everything, the whole screen, and we are setting the whole screen to purple. So we can see that in action if we run here. Let's see here, and there we go. So everything here is like a pinkish purple, and we're running at 60 FPS, 60 milliseconds per frame. That's pretty good. So for the ray tracer, we probably want something similar to this screen fill, but something a bit faster. So what we will use here is a mem set, where we will set the pixels to value 0, and of course that will have a 4 times width times height size. Basically does the same thing, but now it sets everything to black instead of purple, and it's quite a bit faster, so that's always good. Okay, we'll also need to know our screen ratio, so let's create a float ratio, and that will of course be width divided by height. This is not always 16:9, so we need to keep this in mind. Of course, once we make a ray tracer, we need to know exactly how wide and how high our screen is going to be. So for now, what I want to do is I want to have a screen width that is always equal to 1, and then I want a height that is basically proportion to this width, right? So it is width divided by the screen ratio will give me the appropriate height. Okay, so let's start off with the position of our camera. We'll just call it something like campus, and this will just be, let's say 0, 0. We'll keep it nice and simple, right? And then minus 16.0f. So it's nice and a bit to the back. So this way we can see anything that is inside of the positive Z space. That's pretty good. Now, for our camera direction, we want to keep this pretty simple too. So we just want to stare very promptly into the positive Z direction, right? And of course, this needs to be normalized actually, because we might want to change this direction later, and making sure that your literal is always normalized is kind of annoying. So I'd rather just factory F here and then dot normalized. There we go. Then to determine the axis of our screen space, we will first need to do a little bit of linear algebra. With these, we'll also need an up vector, which is of course just 0, 1, 0, right? That is up. And then we can define factory F that the camera X direction is equal to up dot cross and then camera direction. So make sure that you check all of this linear algebra stuff by yourself. It is pretty simple to do. And this is definitely not a beginner's kind of series. So I expect that most of you will be able to at least get around with linear algebra. And you'll be able to verify that this is true. Right, so now we have one vector that points in the X direction of the camera, of the screen face, and one that points in the Y direction. Now, if we move our camera direction, right, so we start to look in another direction, this will still point exactly in the X and Y direction in camera space or in screen space. Okay, we then want to iterate over every pixel inside of screen, and then for every single one, we want to shoot out a ray, right? So for that purpose, it's quite handy to just start off with a vector that will point to the top left position of your screen, then just iteratively sample the rest of the screen from there. So to do this, of course, this will be our top left position of the screen. This will be equal to the position of the camera, of course, which will be camera position, not just position, plus 2 times the direction, the camera direction that we have. This can be anything, but this value here is basically going to determine our field of view, right? So if our screen is further in front of our actual camera position, then we get a smaller FOV. And if the screen is closer to our actual camera position, then we get a wider FOV. That makes sense, right? So this is basically the FOV. We'll keep it constant at 2 for now. Then we subtract half times the camera X. Not 1, because remember, the width of our screen will be exactly 1. So we start in the middle. So we go only to the left by a half. Then we can go to the right by 1 and we get a 1 wide screen. Now we go up by something similar, which will be a half. And again, divide by ratio to get the height that we need times the y direction. From here then, we can start iterating over x and y. So int x equals 0, x smaller than width, plus x. Same thing for y. We iterate over the whole thing. So then we have a loop over the entire screen. From there, we can create a vector again that will go through the screen at the right pixel, right? So this will be basically the pixel position in world space. This is basically a stop left, right, as we described before, plus, and then some width. For us, the width of the screen is 1, right, times x times camera x divided by width. Right, so I hope you see here that we basically normalize x by width. So this is a range of 0 to 1. We multiply that by the actual width of our screen, which is in this case just 1, so you could leave that out. And you multiply by the actual direction that we're going into. Of course, if the screen is, or if the camera is pointing directly into the z direction, camera x and world x are the same thing. But again, if we move our camera around, then this will not always be true. Do the same thing, but of course opposite for y. So -1 divided by ratio, don't forget that because we're talking about height now, times our y, times our cam y, and then divided by height. There we go. And that's that. From here, we can actually create our ray direction. Now, it's actually quite useful to have a ray struct as well. So let's create that really quick. Right, so let's go up here. And under our meshes, we can create a struct. Now, it doesn't really matter how you do this. I usually like the old style of type-def struct, and then we can call it array type, and define that as array. And of course, this thing can have a vec3f pos and a vec3f direction, and then also a float t that will determine the distance that our ray has to travel in order to hit something. I think position and direction speaks for itself, right? Okay. So let's create our ray. So we can say ray. Oh. And ray.position is going to just be the camera position, right? That's where we start as the ray. Then ray.direction is going to be our pixel position minus the camera position, right? That is the position where we cross the pixel and the position where we start our ray. So clearly that's the direction, but we need to normalize this. This is not always length 1, so let's normalize it. There we go. And then the closest distance, or the distance to the closest object, we need to initialize that to something. So it's really useful to initialize this to like positive infinity, basically. Doesn't really exist for C++ as far as I know, so let's initialize it to 10 to the power 30, and that'll be that. If the closest object in our scene is actually 10 to the 30 away from us, well, that is so far away, surely we can just ignore anything behind that wall, right? That is kind of ridiculously far away. From here, we can iterate over every triangle that we have in the scenes. We can go int I is smaller than all of the vertices that we have. Divided by 9, of course, because every triangle has 3 vertices, but every vertex has 3 coordinates. So we need to divide by 9 here. Remember that vertices is actually just a float array and not a vector3 array. And then we increment I. And then here we need to do an actual ray triangle intersection. There are a whole bunch of algorithms that can give you the result of a ray triangle intersection. We will be using the Müller-Trombor algorithm. I'm not sure if I'm pronouncing that correctly though, but I'm sure it will be fine. I'm not going to completely explain everything about this algorithm. Of course, I'm also just a normal guy who kind of just copied this from the internet. But there's a basic idea behind it, right? So let's talk about the basic idea. First of all, we take an array, and we take in a triangle, but let's just take in a triangle index because we have access to the actual triangle list from here, so why not? From there, we can first determine every single triangle vertex. Now, we first need to check if the triangle that we're trying to intersect and the array are parallel. If they are, then there is no way that we are ever going to intersect it, or it's going to be like almost infinitely far away. That's no good. So we want to kind of avoid this edge case, so we need to check for it. Next up, we can just check whether our array intersects the triangle outside of the triangle. So it intersects the plane of the triangle outside of the triangle. Otherwise, we can actually calculate the distance as control t, and that is f times edge 2 dot q. And then we can just say if t is actually greater than 0, because of course if the intersection is behind the camera, then we don't really care. So if t is greater than some very small distance, sure, we don't want it to be exactly inside our camera either. It probably doesn't matter that much. But anyway, then t is just equal to the max of array.t and t. Min. I'm very, very sorry. So then the distance to the closest intersection is of course the smallest of either what we already had or our new distance to this intersection. Okay, and that is the Muller-Trim-Bohr algorithm. Fairly standard, fairly standard. We can invoke this though, so we can say triangle array intersection with our array and our triangle index, which is just I in this case. And then we can just do this for every single triangle that we have. Then we will find some value for array.t. And actually, in fact, if array.t after this is smaller than 1e30f, i.e. we found a closer intersection for it, then we can actually write to our pixel buffer. So we can then say something like pixels. Then we can say for, actually, let's create an index here that will just help us a little bit. idx int index. So we can say something like the index in our buffer, right, will be x plus width times y. And then we can just use for times index plus 0 for red. Let's put red at 255. We have green, blue, and alpha. That's set green to 0. And then again, we get a very nice pinkish, purplish color for our triangles. Nothing fancy, no color per triangle, and no texture for triangles, just something very similar. Okay, so again, in our main, when we render in our loop, we run, which is this function that we just made, right? That's this ray tracer function. And then with that pixel data, we draw it, right? So we get this pixel data and we put it inside of this texture, and then we render this texture. Now, if we run this right now, we'll see that we are still at a solid 60 FPS. That's great. But it's a black screen, right? And that is because actually we don't really have any triangles right now. So we might want to change that. So let's do that right around, well, let's do it here, that's probably fine. So let's make an actual triangle. So we can make a float triangle, and of course it has 9 floats in it, as we just established. And I want it to be in the middle of the screen, but I want it to be like not too regular, right? It has to have some wonk to it, let's say. So let's start off at -1 in the x and -1 in the y and -1 in the z. Then we can make an edge to the plus side in x, so we can do plus 1.0f. We're still negative in the y, and we can maybe do something silly with z, so we have some depth in there. And then at last we have our top vertex, so we get a nice and a regular triangle here. 0, then of course plus 1.f in the y, and then again something silly with depth. And there we go. I think that's a pretty normal triangle. From there we can do ray tracer and then add mesh, which is of course triangle dot. Right, so that's just the buffer itself, just the array itself. And then the size, of course, is 9 because we have 9 floats in there. Okay, so let's see how this works. Do we get a picture? As a matter of fact, we don't. Right, so I found our little issue. Of course, if we divide two integers by each other, we are basically going to get garbage. So instead, here we go. Cast them to float, and that should be a whole lot better. Okay, another problem, this should be u plus v. I copied a little bit too quickly, and that should do it. So let's see. Yes, and there we go. Although for some reason, oh, right, I see. Wanted to say for some reason it's red and not purple, but of course we forgot to change these indices, and there we are. Ah, much better. So you'll see that it takes a little bit longer now. So one frame is about 80-90 milliseconds, and it takes about 52-55 frames per second to render this nice triangle. But at the very least, it works. So that's always a good thing. Now we can do one more thing to kind of show you what I was talking about with this camera direction, where we kind of move it around and then the X and Y of the screen space move around accordingly. So what we can do here is, for instance, we can set our mem setback. I did that for testing purposes. So what we can do here is we can have some sort of float t for time this time, right? It's going to be 0. And then we can say that our camera direction is just 0.1f times std cosine of t, and y is going to be the same thing but std sine of t. So we're going to get a direction ray that is going to kind of move around like this, right? So it's going to point in a clear z direction, but it will have some offset in x or y. That's going to do quite nicely. Of course, we need to update t here all the way at the end, so t plus equals 0.1f, something like that, or 0.002 actually, otherwise it's too fast. Let's go for that, and there you go. So now you'll see that we don't get any weird distortions. The triangle just kind of moves around in a circle as it's supposed to. So that's great. That's great. And of course you can make it faster if you increment t faster, but it's not the point. Right, and that is going to be the basis for our ray tracer. This code, of course, you can also find on the GitHub page, so please head over. There are 2 links to GitHub now, one for the branch with the base code and one for the branch with this code on it. For the next episode, I think we should really start looking into some of the algorithmic complexity first. This one is the simplest to get into and also usually the most rewarding. So if you have an algorithm that is very slow, then it doesn't really matter how much SIMD you're using, it doesn't really matter how much cache and memory alignment optimizations you do. If the algorithm is bad, you'll always be worse off than if you just used a better algorithm. So that's what we're going to be looking into next, and I hope you are all just as excited as I am. And yes, that is it. So be sure to subscribe if you don't want to miss the next episode or any of my other videos. Head over to my twitch.tv/NoNumberman channel and check out my streams there. I stream quite regularly and we do all sorts of wacky programming stuff there. And lastly, we have a Discord server. If you have any questions about this video or another video or anything at all programming related, then head over to the Discord server and ask away. We have a wonderful community and we all love to help you out. All right, hope to see you in the next episode, and goodbye.